What's going on, everybody? This is Mr. Diamond, and we are back here to talk about Section 3, Representing Bonds. Now, what we're really going to focus on here in this first section is going to be Lewis dot structures. We're going to start with just for atoms, then for ions, and then for ionic charges. Or ionic compounds. We're not going to get to covalents. Covalents get their own section. They have a lot more going on. There's a lot more stuff that we'll need to talk about in relation to that, and it'll be a little bit more in detail or in depth than the other section here. So Lewis dot structures are something you're probably familiar with. I'm assuming that you did at least something kind of like them in integrated science or one of your previous classes. They're the most simple and common way of representing atoms and their electrons. And this is where you have to know the number of valence electrons. Remember, I told you those were the two things. Ionic charges are super important, or predicting ionic charges, predicting valence electrons or knowing valence electrons was equally important too. It's going to come up right here. As a reminder, you can just count over the columns. All of the D block and all of the F block are 2, and then otherwise it goes 1, 2. You skip over the D block because that's all 2, and then 3, 4, 5, 6, 7. Last column is 8 with the exception of helium. By the end of this, you should be able to use Lewis dot structures to represent single elements ions, covalent bonds, or covalent compounds and ionic compounds. So the simplest thing to do is single elements. You just start by writing out the element symbol, and then you add dots one at a time going around the sides until you have added the appropriate amounts. Important thing is, remember, you're still following the whole rules of don't pair electrons until each one of them has each one of your orbitals has a single area that could be located or could have electrons in it, which is why you fill them in 1, 2, 3, 4, and then 5, 6, 7, 8, and you kind of go around as you add them. So we're going to draw the Lewis structures for fluorine and calcium in my example video in a moment. For ions, you just need to change the amount of electrons and indicate the charge. To change the electrons, just remember the rules we talked about last chapter. Positive charges, which are cations, because cats have paws, you subtract that many electrons, and then negative charges, you just add that many electrons to it, because electrons are negative. And then you indicate the charge, and you put the structure in brackets. Brackets is the way that you indicate that something has a charge, and then you put that charge outside of the bracket. Again, I'm going to do these two examples here, so I'll be able to show you what that looks like, and you'll know how they go. For ionic bonds, you're going to indicate the atoms are connected to each other due to electrons being stolen. So we can indicate using colors to make it really clear, but you can get away with just using a pen and pencils. I'll show you how this works with a few examples. We're going to draw the Lewis dot structures for NaCl and AlBr3, and I'm also going to explain to you the process that occurs for an ionic compound being formed. So this is a pretty short video so far. What I'm going to do here is I'm going to go ahead and pause this recording because I think that's the last slide I have for this. Yeah, I'm going to pause this recording, and then I'm going to try to get my demonstration set up so I can actually talk you through that demonstration really quick. So there's going to be a quick jump. I apologize for that. All right, everybody, welcome back. I apologize for that very brief pause. I forgot that I've updated since I got a new mic. I had to switch my my audio over on my recording software. Let me turn off autofocus also, because that's a pain in the butt. Camera control, no autofocus. Let's down there, apply that. Okay. And we're okay. We are good. Okay, so I've got 3 colors. I'm only going to be using these 2. I'm going to use red and green because hopefully those will show up the best on camera. And we're going to be doing all of the examples that were listed out in the notes for Lewis dot structures. If you have your periodic table nearby, you are going to want your periodic table for this. Will make a lot of these things a lot easier. And I'm going to pull one up just so I can make sure I don't just run from my memory and accidentally make a simple mistake. Okay, so the first ones that we're going to do are fluorine and calcium. So all you have to do for ones that don't have charges associated with them is you need to write the element's symbol. So for fluorine, I've got an F, and then for calcium, I've got a Ca. And then we're going to write the number of valence electrons as dots, but we're going to go around and we're going to add them to each side. There could be a maximum of 8 in this case because this is not hydrogen or helium. Those are the only ones that could have only 2. So fluorine is in the 7th column over. It's right next to the noble gases. So it has 1, 2, 3, 4, 5, 6, 7 valence electrons. I'll put that kind of so it's in the middle again. So we've got 7 dots around it. Let me actually zoom in a little bit since I'm not going to need this whole page. And I apologize, everybody. Haven't had to do this from home in a little bit. There we go. Much clearer. Okay. Now, one question that I usually get on this is, do you have to go in this order? Like, does the dot that's alone have to be over here? And the answer is no. As long as 3 of the sides have 2 dots and 1 of the sides has 1 dot, I do not care which of those sides it is. Same thing with calcium. So calcium's in the 2nd column. So we're going to go 1, 2. We're going to put them separate from each other. Now, you could have put them across from each other. You could have put them adjacent to each other on any of these positions. As long as there are 2 dots that are clearly not on the same side, that is all I care about in regards to this. That is all you have to do to make sure that you've got your calcium Lewis dot structure done. Okay, for our next one, we've got boron. So I'm going to go ahead and write boron. And I'm going to go ahead and write magnesium. Now, boron, looking on the periodic table, normally has 3 valence electrons. It's in the 3rd column over. Or 3rd column over, ignoring D and the F block. But it's got a -3 charge. So since it has a -3 charge, -3, and it actually has a 3- charge, which is technically the correct way to write it. And that's going to be really frustrating for some of you guys. I'm not going to nitpick you, and I'm not going to count points off if you don't do it in this order, but this is the correct order. It's technically not a -3 charge. It is technically 3 negative charges associated with it, which since it's 3 negative charges, that means it must have 3 electrons in addition to the 3 that it normally has. So it normally has 1, 2, 3, and then because it has a 3- charge, we're going to add 1, 2, 3 more. So it has a total of 1, 2, 3, 4, 5, 6 electrons. And then because it has a charge associated with it, we're going to go ahead and we're going to put the whole thing in a bracket. And we're going to put our 3- on the outside. Again, you could do -3 instead. I'm not going to count it wrong if you do that. But 3- is the correct way to write it. Okay, for magnesium, magnesium normally has 2 electrons. It's in the same column as calcium. It's right above it. But it's got a plus charge. So a plus charge means that it must have lost one of its electrons because it lost something that's negative. Subtracting a negative makes something positive. So losing an electron means we're going to go, instead of it having 2, it's actually only going to have 1 single lonely dot. And then because it has a charge, we're going to put it in brackets. We're just going to write that charge right on the outside of it. So again, anytime there is a positive, you removed whatever number is associated with it. If there's no number, you just assume it's 1. Anytime there is a negative, you add that much. If it's no number associated with it, you just add 1 to the electron count that you've got. If you get something that goes down to 0, you can just do none and put it in brackets. Or I will also accept 8 and put it in brackets because it's gone down to the previous level, which means that level will have 8 valence electrons. Okay, these next 2 are the ones that are a little more in detail, and these are the ones where I'm going to use my my red and my green here. So the first thing that I'm going to do is I'm going to show the process. So the process of ionic bond formation. So I'm going to start making sure it's on in focus. So I've got Na, and Na, based on its position on the periodic table, has 1 electron, 1 valence electron. And then Cl based on its position on the periodic table, has 1, 2, 3, 4, 5, 6, 7. So we've got 7 electrons here, 1 electron here. So the first step, the first thing that's going to happen in the formation of an ionic bond, let me move my this thing out of the way. I apologize if that made a loud noise for everybody. Okay, so step 1 is that chlorine will steal sodium's electron. So this electron here that was attached to sodium is now going to go to chlorine. Step 2. Chlorine and sodium are now charged. So I now have a bracket. Sodium has lost 1 electron. So it has a positive charge. And then chlorine has now gained an electron. So notice I left that dot red because that's the one that came from sodium. So it has a negative charge. And then finally, step 3, electrostatic attraction. Or you could just say positives and negatives attract. There's an electrostatic attraction, or positives and negatives attract. So Na and Cl bond ionically. So the way I will usually write this, if I have colors, it makes it a little bit easier. We're going to do this. We're going to pretend that's green. And there you have it. They have ionically bonded to one another. Or you could also write it as something like this is what some of the kids came up with last year that I really liked. This is a way you can represent it without actually having color involved. This shows that you know that that electron did not originate on that Cl. You're kind of indicating that that electron came from somewhere else. Okay, so now that we've explained the process, either one of these is fine. If I come up here, I'm going to go ahead and redraw it. So I've got my Na. I've got my Cl. Or and I know it's a pain to use all these colors, which is why I'm giving you the option of, as long as you indicate that this electron here, sorry, didn't move it down, that this electron here came from the sodium, you are good. Okay, so that's the process explained, but normally you're not going to want to work through all of this information. So instead, we're going to use a different method that'll take up a little bit less space for our AlBr3. So step 1, I'm not going to actually write out steps this time. So Al has a predicted charge of +3. Br has a predicted charge of -1. Al has a predicted charge of +3 because it's in that exception slot. It always has a charge of +3. It's the staircase off the staircase. Br is in column 7. It's one step away from being a noble gas, so it has a -1 as its charge. Looking at the structure that it's going to make, or looking how it's connected to each other, our Al has 2 valence electrons, and our Br has 7 valence electrons. So what's going to happen here, 3 valence electrons, not 2. So what's going to happen here is we're going to have one Al and I'm going to make this a little bit big this time. And that Al has lost all 3 of its electrons. It had 3 electrons that would have been here, but they have been taken. And each one has been taken by a bromine. And so these bromines all will have their 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3 electrons. 1 to each of them that came from the aluminum. Now, the process would work the same here as just a very quick version of it. If I have Al 1, 2, 3, each one of these electrons is going to go to one of these chlorines. That will drop aluminum down to having 0 outer layer electrons, which is the same thing as having a full layer on the lower level. And then chlorine will go to 8, which will be, or sorry, these were all bromines. Sorry about that. So all of these electrons, 1 each, will go to a bromine. That will mean that the bromines have an octet. That will mean aluminum drops to a lower layer, so it will represent or look like neon. Now, the other way you could draw this, if this is just not your jam and you're just not feeling that, you don't like the way that looks, you could also draw it like this without color. And I'm drawing it this way, not just because I'm out of space, but because I don't want you to just get locked into the thought of like, oh, they have to be like right next to each other. Personally, I think this way, like in my head, this way is nice, it's neat, it's concise, it tells me that they're attached to each other, the colors show me where all the electrons went. So I like it that way. But you don't have to do that. You could have also drawn this one as just that. You could have just had them close enough to each other. And as long as you don't have the charge, because again, once these things have stuck to each other, they're actually no longer going to have that charge. It's still getting across the same idea. You just need to have them close enough to each other that it's very obvious that you are not talking about individual separated things. Like in these cases over here, you are talking about things that are close enough that they are attached to one another. So you could have put a BR all around this. You could have put them all listed over here. You could have put them all underneath it. As long as they're all close enough that I can kind of tell what's going on, you should be fine for it. I am just partial to this method. I feel like it's nice, it's neat, and it makes it a little easier to remember exactly what's happened. And it's different enough from this that you don't have the worry that like, or it's different enough from this that you don't have the worry of whether or not you've like separated them out far enough or anything like that. So that's how to do Lewis dot structures. I apologize that I kept forgetting to move this around in enough time. You will also, in theory, be asked about this on the test. This could come up. I think it's also on the worksheet. It could ask you questions like explain the process of ionic bond formation using, and it could give you 2 elements. This is the process they're looking to. Whatever is most likely to be positive, whatever is the metal, is going to give up its electrons to the things that are non-metal. That will create 2 things that are charged that will then stick to each other because of electrostatic attraction. Anyway, I hope that makes sense. In the meantime, this has been Mr. Diamond. Hope you have a great day, everybody. Email me if you got any questions. This is me signing off.